So this is the Arcosanti transition video. Just a quick background about Arcosanti. They are a urban laboratory located north of Phoenix. So what that means is they test concepts for future societies, and how that relates to the EPICS program is that they have been doing a project with us for the last year about taking their gray water and then reclaiming it to grow plants with for human consumption.
All right, so Arcosanti has two gray water tanks, and so from the first tank, all the gray water flows through there, and it flows through a turf-type filter, which takes out most of the debris, and then flowing from the first tank to the second tank, it goes through a biodisc filter, which takes out more debris and particles. Then from there, the gray water can be used for other purposes on the plant.
Yeah, so it goes from the first tank to the second tank through a turf tight, and then from the second tank, before Arcosanti's been using it, they put it through a biodisc filter later on in this flow line. So all the water that this project will be working with will come from the second tank here after it's gone through the turf tight filter. And here's a quick picture about the different application sites they're considering. They haven't made a solid decision yet, but there's things here, here, over here, up here. They're still making up their minds on it, and there's different things they're considering, such as visibility, area, sun exposure, and how far out of the way it is so that nobody comes in contact with the gray water flow lines.
In order to get a better understanding of the microorganism levels at Arcosanti, we had an independent water test done with the aquatic consulting and testing. So as the results show, Arcosanti had a high level of E. coli and high turbidity. We decided to go with the Class B definition of the water just because that's easier to plan for. But Arcosanti's water levels were so bad that we have to actually go and filter the water ourselves, as we will show next.
Based on the test results that we received, we realized that the source of water is very concentrated with turbidity and E. coli and other fecal coliform. So with that in mind, we decided to collectively do research on different methods of filtration, and we found out that coagulation, continuous chlorination, and UV filtration were probably the three best bets. From there, we plugged that into an AHP design matrix with different parameters ranging from cost to health effects. And from that, we found out that continuous chlorination was probably our best option. It scored high pretty much on every single parameter and had an average of about a 7.52. Meanwhile, coagulation and UV filtration scored about a 6.
So here's a quick diagram about how continuous chlorination works. So you have different chlorine tablets that stack up in the tube here, and then depending on how dirty your water is, you can lower the chlorine tablets further into the waste flow stream, which is flowing parallel to it, and the further down in the dirty water stream you put the chlorine tablets, the more of them will dissolve, thus the more chlorine in the water, the better you can treat your water. And if you want less, you can push it up a little bit or even put spacers in between the chlorine tablets here. And then there's also another cutaway figure just to give you another look at it. So taking all this data, we made a MATLAB simulation of it, taking into account of the different contaminants that were mentioned previously. We have some flow data from Arcosanti themselves on their system. We also looked at a couple different plants, namely dwarf apple trees, just because our community partner mentioned how they were looking to do a miniature orchard, which usually means dwarf plants, and comparatively there's a lot of data on dwarf plants. So we also took some climate data, put that all into a model, and then output it a couple different things. So right here are the two biggest graphs, the cost of the system and the food produced. So as you can see from the graph, about 1 year running the system with mature dwarf apple trees will get you about 1,600 pounds of apples over the course of that year. and at the same time, running the system over the course of 1 year would cost about $1,500 total. However, a lot of that is the initial cost here. So realistically, it's only about $1,000 to run the system over that year. And this initial cost is made up of the cost of buying the plants themselves and planting them. Other costs of the system include maintenance for each one of the plants. It was estimated that each plant would cost about $100 in maintenance over the course of the year, between plant upkeep, harvesting, doing fertilizer, just small things like that. And then another big cost of the system was the chlorine itself, which we'll get to in this graph here. So based on we had flow data for 5 different months from Arcosanti, so we plotted each one of those here. And then based off of that flow, the turbidity was how much chlorine we would need to filter that. So for example, 1 month they used about 400 gallons of water, and in that same month you need about 7.5 pounds, 0.075 pounds of chlorine to treat that. And that 0.075 pounds of chlorine would cost about 17 cents or so from a source we found on Amazon. And so combining that all together, we found that, running the system over the course of a year would only be about $1,000 with everything combined, or if we were to do it over a 4-year basis with just 10 apple trees, we could produce about 6,500 pounds of apples, while at the same time only costing a total of a little over $4,500. That's the end of our presentation, pretty much. Our community partner expressed that they don't want to continue this next semester due to the project costing more than they initially thought, because they thought they were going to have cleaner water. And so they're really just not interested in putting that much more into it and would rather direct their efforts elsewhere. Thank you. Goodbye. I hope you learned something.